Oh, welcome guys. Welcome guys. So in this video, let me just solve this very old school electrodynamics problem. Because so many people like to ask me this question, so I'm bored that I want to just make a video. So let's say we have a ring with charge Q, and the radius is A, and the center is O. Okay, so let's say call it O. And at this point, the distance R. Okay, so let me call this point P. Okay, so I can assume that Q is greater or equal to 0. But if Q is less than 0, then the answer should be the same. Okay, so our point is that we just want to solve the potential at P and the electric field at P. Okay, so let's just do it. Okay, so our K is basically 1 over 4 pi epsilon 0. So this is just some convention. So based on what you learn, if you're in the first year of the college, then you should use K. If you're in electrodynamics, then you can use 1 over 4 pi epsilon. Okay, so let's say Vp. So Vp is defined to be what? If it's defined to be the total charge, right? dq. Do integration of this K and the distance, right? So, but if you see for each P, for at P, right? Each point, the distance to P is just the same, right? It's always a squared plus r squared. Take a square root, so we just take it. So it becomes K dq square root a squared r squared. So it's just KQ square root a squared plus r squared. Okay. So let's talk about electric field. So there are various ways. Okay, so if you're studying the second year of the electrodynamics, then you can use you can use this gradient of this guy. Okay, and then you get the answer. Okay, so actually this is the first way to do it. So we do the partial potential partial r, and take a negative sign, right? So the answer will be a squared plus r squared 3 to the 2 kq. Remember that we will get the 2 here, right? But we get a 2r here, so we cancel. Okay, so this is the answer. Also, if q is positive, then the electric potential, the electric field is these directions. Okay, so this is the correct directions, and also the correct answer. So this is R. Oh, A squared. Okay, maybe let me just write it carefully. Okay, but maybe if you're not the second year electrodynamics, so you don't know the gradient or something, or not. So let me assume that you don't know it. So the second way to solve this EP is that we draw electric field, right? So electric field, at this point, this electric field will give you these directions. Then at this point, it will give you these directions. So you see that all the directions other than R will be cancelled. So all you need to know is just project it into R, right? So that's your EP will be dq 4 pi epsilon naught. Okay, maybe I use K for convenient. K right, force. Okay, so the denominator is a squared plus r squared, right? And so this is dq. So the EP will be k dq this way. So this is just this guy, right? But we do the projection to x, right? So let's say this angle is theta. Okay, this angle is theta. So you see this theta is here, right? So theta. So we just times cosine theta and do dq, right? So remember the cosine theta is constant now, right? So k divided by a squared plus r squared, and cosine theta. So integral dq. So this is q. So it's kq a squared plus r squared. What is cosine theta? Is r divided by this, right? So it's r divided by a squared plus r squared. So answer will be kqr a squared plus r squared. Right, so it's the same as this. And then remember so this is a scalar, right? If you want to write it as a vector, then you just make these r directions. Okay, so the same. Okay, so that's it. Because people like to ask me, so let me just produce the different method to solve it. So let's call it 2.2. Okay, so be sure to subscribe to my channel. I'll see you guys in the next videos. Yeah, thanks.